So, hello everyone again. This is lecture 2 part 1 of semiconductor electronics materials devices and simple circuits. In the previous discussion we were in the second point, that is classification of metals, conductors and semiconductors. We will go with further discussions on this topic only. So, I am Sameer Lavankar. Let us begin our discussion. Okay. So, right now we have already been done with the introduction part, as in the history of the semiconductor devices, as in how it was being implemented, what was the actual size before, how it has been discovered, what were the things which resides behind the complete discovery, etc. Right now, in the previous class we started with the classification of metals, conductors and semiconductors, in which we understood basically what is the difference between metals, conductors and semiconductors, on which of the basis these are being classified. The complete discussion is not over. We were in the previous discussion at the last point, we were discussing about the chemistry involved with in these things, in the valence band, conduction band, etc. So, let us start that discussion only, and then we can go on to next topic, that is intrinsic semiconductor and extrinsic semiconductor. Okay. So, let us start our previous concept only. So, classification of metals, conductors and semiconductors. Okay. So, we will try to make you understand whatever is written here. For now, just please listen or please observe just the iteration part only. Okay. So, let me start it again. So, let us consider what happens in the case of silicon or germanium crystals containing n atoms. Let us say there are n atoms of silicon, or let us say n atoms of germanium. So, for silicon the outermost orbit is the third orbit, n is equal to 3, while for germanium it is the fourth orbit, n is equal to 4. Quite evident, it may be known to you if you have in the chemistry classes also. So, it is quite evident, because you can even see in the periodic table that silicon has a outermost orbit of 3 and germanium has an outermost orbit of 4. Okay. The number of electrons in the outermost orbit is 4, quite evident, as it is 2s and 2p electrons. Okay. Hence, the number of outer electrons in the crystal is 4n. How it is 4n? Because the number of atoms are n, therefore 4 multiplied by n gives you the total number of outermost electrons in that complete n atoms. Okay. The maximum possible number of electrons in the outer orbit is 8, 2s and 6p electrons. Okay. So, previously it was saying that what are the number of electrons actually present there, and now they are talking about the amount of electron which can be maximum present. So, maximum can be calculated using the chemistry concepts. So, finally what we got is that using the Bohr's model, let us say we are talking about Bohr's model here, then the maximum possible number of electrons in the outer orbit is 8. So, 2s and 6p electrons. Okay. Hence, from the above 4 points, what we concluded is, above 5 points, what we concluded is the 4n valence electron, for the 4n valence electrons, these 4n valence electrons, there are 8n available energy states. So, these electrons can go and reside in any of these energy states. So, if they are in some energy state, hence the amount or the concept to be utilized is in this error. So, this way, not error, this way. So, how it is being said, what are these energy states, etc., will be explained very clearly in the subsequent slides. For now, what we got is that okay, there are 4n electrons, we can say that there are 4n atoms, sorry 4n electrons, let us say I say n is equal to 2, then there are 8 valence electrons and it can reside actually in 16 available energy states. How they will, what are these energy states, how will they will be residing, etc., will be dealt in subsequent points. For now, we have concluded till this point. Okay. Let us move on with the further discussions now. So, these 8n discrete energy levels can either form a continuous band, or they may be grouped in different bands depending upon the distance between the atoms in the crystal, and this is the complete concept which is being involved here. So, what they are trying to say is that either energy state, as the name suggests, it is energy state, right. So, energy state is nothing but the variation of the positions of the valence electron which leads to the energy being propagated or being captured by the electrons. Okay. To make it an easy way, what does it energy state basically means is, so basically this is also an energy state, this is also an energy state, this is also an energy state, and this is also an energy state, right. So, basically the way in which these electrons reside leads to a different or an or discrete energy state which is being explained here. Okay. So, what does it try to say is, so in vague term what you can say is there are 8n discrete energy levels. So, these can either form a continuous band or they can form a discrete band. So, this has only been explained here. Okay. So, how it is being, so as we can see that this is a discrete band, right, and these are continuous bands. Continuous as in they overlap or they have a very large gap, large wide area for its propagation, etc. As in the valence electron can move in that complete continuous band area. In discrete as in it is in very small space. So, that is being explained in this type of energy states. Okay. So, these 8 discrete energy levels can either form a continuous band or they may be grouped in different bands depending upon the distance between the atoms in the crystal. Okay. So, how it is being discretized depending upon the distance, we will try to I will try to explain to you. For now, let us look here only. So, at the distance between the atoms in the crystal lattices of silicon and germanium, the energy band of these 8 states is split apart into 2, which are separated by an energy gap Eg. So, this is what we can say that one of the definition or one of the explanation of how we can understand what is this Eg being explained here. Okay. So, at the distance between atoms in the crystal lattices, so let us say this is the distance between the atoms in the crystal lattice of silicon and germanium, the energy band of these 8 states is split apart. So, basically some will be residing here, some will be residing here. So, because there is an energy gap between them, it can be also called as a state, because state is something in which the electrons are residing, right. So, and it is been explained here that for semiconductors such as silicon and germanium, in our case to understand this complete concept, what we are trying to say is that they are split apart and they are split apart by an energy gap Eg. So, this is how you can understand the concept of energy state and energy gap Eg. Okay. Please remember the thing which you need to remember is, one thing is that there are 4n valence electrons and there are 8n available energy states. Okay. Fine. So, next thing is the lower band, which is completely occupied by the 4n valence electrons at the temperature of absolute 0 is the valence band. So, this is basically the valence banding explained here. So, as it is also saying, it is lower band, quite evident lower band, which is completely occupied by 4n valence electrons. So, as you can see, these blue dots are nothing but your 4n valence electrons here. Okay. At the temperature of absolute 0 is the valence band. The other band consisting of 4n energy states. So, quite evident, please be very clear in understanding this energy and energy and valence electrons. Okay. So, there were 4n valence electrons, right. If there are 4n electrons, those valence electrons would be residing somewhere. Let us say for the temperature 0, they are residing in something called as valence band. That means these 4n valence electrons are residing in 4n energy states, fine, and these other energy states been explained here. But there can be more energy states also, where because we understood right now that there are total 8n energy available energy states. That means that the remaining 4n energy states would be residing in or would be present in this above band called as conduction band. So, this is only the difference between these valence electrons and energy states. Quite evident, if there are valence electrons, then that electrons will be residing somewhere, that residing at the initial stage is called as your valence band. Okay. So, these are nothing but the places or energy states. So, these are basically 4n energy states here and 4n energy states will be here. Okay. Fine. Then, so this thing has also been explained. Next thing is the other band consisting of 4 energy states called the conduction band is completely empty at absolute 0. So, at T is equal to 0, what they are trying to say is that temperature at T is equal to 0 Kelvin, what happens is that 4n energy states are here, 4n energy states are here, but this is well occupied at 0 temperature, at absolute 0 temperature, but and this is not at all occupied at 0 temperature. Okay. One of the reason of this can be said as in there is no energy excitation, there is no energy imparted into the valence electrons, hence they reside in the valence electrons only. When the energy will be imparted such that energy is greater than the energy gap or equal to or approximately equal to Eg, then these valence electrons will jump and move on to the conduction band. Okay. Let us move on. Now, consider that silicon. So, now we are trying to understand this complete. So, basically let us pause this complete concept of classification now and let us understand this complete band. What is this complete band theory of solids? Okay. So, band theory of solids has to be explained. Please be very clear while please be very careful while understanding this, because as you can see there are I guess 4 regions to be explained here. I guess region A, region B, region C and region D. Yes. So, 4 regions have to be explained. I will go very slowly while making you understand this. So, let us start this concept. Okay. So, consider that the silicon or the germanium crystals contain n atoms. So, as the previous discussion also we were concluding that let us say that the silicon or the germanium crystal are having n atoms. electrons of each atom will have the discrete energies in different orbits, quite evident. Every electron, so let us say this is your neutron, proton, and this is your complete orbit. So, what they are trying to just say is that there will be electrons here, there will be electrons here, there will be electrons here, but these are electrons will be having different energy states, right, and because they are having different energy states, they will be having different energy values. Okay. So, the electron energy electrons of each atom will have discrete energies, discrete as in different energies in different orbits, quite evident. So, in chemistry you may have learnt also that there are different subsequent formulas for finding out the energies of electrons of each atom at different energy at different orbits. Okay. So, from that also we can understand this second point here. Okay. Third is the electron energy will be the same if all the atoms are isolated, that is separated from each other by a large distance. So, what they are trying to say is, let us say there is one atom here, there is one atom here, as the distance is very large, as the distance, let me draw it very carefully. Okay. So, let us say this is the one of the atom, and let us say this is one of the atom, right. So, what they are trying to say is that if this distance is very large, let us say if this distance is very large, then there is no effect of the energy of these electrons on the energy of the electrons residing in another atom. Okay. So, if it is happening, that means that the electron energy for the subsequent atoms, whatever their energy would be the same throughout the complete subsequent changes in time. Okay. But now what they are trying to say is, let us say, but it does not happen in every time. Let us say we are trying to make a, let us say we are trying to make a table only. So, for making a table, the actually material consists of atoms, and these atoms have to be constructed very close to each other, and due to which what happens is that there is a change in the energy of the electrons in any of these, or let us say of the outermost outermost orbit, due to the effect of the nearby atoms. Okay. And there is not even only one atom, there are surroundingly multiple atoms surrounding each of the single atom. Okay. So, this thing was to be explained here. Okay. So, the electron energy will be the same if the atoms are isolated, that is separated from each other by a large distance. However, in a crystal the atoms are close to each other, 2 to 3 angstroms, as I already explained. Please remember what is Armstrong. So, Armstrong is basically 10 to the power minus 10 meters. Okay. So, and therefore, the electrons interact with each other and also with the neighboring atomic core. So, basically due to this interaction there is a change or the variation or the fluctuation in the energy of these electrons. The overlap or interaction will be more felt by the electrons in the outermost orbit, while the inner orbit or core electron energies may remain unaffected. Quite evident, because those are very much constricted, or the attraction of the proton towards the electron are very much higher. So, that the effect of the nearby electrons are not much on these inside electrons. Majority of the influence of the fluctuation happens for the outermost electrons only. One of the reason is that because it is the most far apart from the inside neutron or the proton, and second thing is because it is most far. So, therefore, there can be direct interaction between the outermost electrons of the both atoms, both different atoms. So, the overlap or interaction will be more felt by the electrons in the outermost orbit, while the inner orbit or core electron energies may remain unaffected. Okay. So, that is the only explanation explanation being done here. Therefore, for understanding electron energies in silicon or germanium crystal, we need to consider the changes in the energies of the electrons in the outermost orbit only. So, finally, what is the conclusion of this band theory? We are only considering the changes in the energy of the electrons in the outermost orbit only, and then we are trying to understand what actually happens, what are these energy states, etc. Okay. So, this is the first conclusion, and this is the conclusion of this slide here. Let us move on to the next slide now. Okay. So, now let us first of all understand for silicon, and then side by side for germanium also. Okay. So, for silicon the outermost orbit is the third orbit, that is n is equal to 3, which we previously discussed also, while for germanium it is the fourth orbit, that is n is equal to 4. Okay. The number of electrons in the outermost orbit is 4, that is 2s and 2p electrons, similar as before. Hence, the total number of outer electrons in the crystal is 4n. The maximum possible number of outer electrons in the orbit is 8, that is 2s and 6p electrons. So, out of the 4n electrons, 2n electrons are in the 2n s states and 2n electrons are in the available 6n p states, quite evident. So, basically there are total 8n possible number of states, right, out of which there are 4n valence electrons. So, what they are trying to say is, let me make the picture much more clearer. So, basically there are 8n available energy states. So, for now what they are doing is they are dividing it into two types, right. So, there will be energy state due to 2s electrons and there will be energy state due to 6p electrons, right. So, therefore, what happens is there will be 2n s states, right, and there will be 6n p states. Okay. Now, what they are saying is, what the new thing is that they are saying is, so there is the total number of outer electrons are 4n. So, basically what they are saying is the 2n electrons are residing here, 2n electrons are here, and out of the 6n p states 2n electrons are here. That means 4n p states are vacant at a particular instant of time. Okay. So, this thing has also been explained. So, that means this thing is done, this thing is done, this thing is done. Okay. So, out of the 4n electrons, 2n electrons are in the 2n s states, orbital quantum number L is equal to 0 and 2n electrons are in the available 6n p states. Okay. So, therefore, 4n p states are always vacant at any instant of time. Only the thing is, because due to the energy fluctuations, some of the electrons may go to some other valence states, some other energy states, and there can be a change in the what we can say actual place at which this valence electron was residing before. Okay. So, obviously some p electron states are empty, which I already explained to you. Obviously some p electron states are empty as shown in the extreme right of the figure. Okay. So, this thing is explained. Next thing is, this is the case of well separated or isolated atoms, region A of the figure. So, this is the complete discussion which we did was for the region A of the atoms. Okay. So, what was happening here, as you can see here, that there is one state here, there is one state here which is denoted by L is equal to 0, there is one state here denoted by L is equal to 1, okay, for which 2n electrons are residing here and 2n electrons are residing in the 6n states. Okay. Because these are isolated atoms, that is why we are calling it, because they are discrete. As you can see, there is no continuous band here, only a single line is being drawn. So, basically the electrons are only residing, let us say, on this particular discrete lines only. So, basically therefore, this is the case of well separated or isolated atoms, as in the atoms are far from each other. So, that is region A. What is region A? Region A is the well separated or isolated atoms. Let us move to the next point now. Okay. Now, suppose these atoms start coming nearer to each other to form a solid. Okay. So, let us say now we are trying to form a solid. So, what will be happening? These atoms, so there will be, let us say these are atoms only, these lines depict the atoms only. So, these are trying to come close to each other. Okay. So, suppose these atoms start coming nearer to each other to form a solid. Okay. The energies of these electrons in the outermost orbit may change, both increase and decrease due to the interaction between the electrons of different atoms. Okay. So, the energies of these electrons in the outermost orbit may change, because we have already been discussing this topic that there is fluctuation in the outermost valence electrons due to the activity of the nearby atoms. Okay. Therefore, the energy of these electrons in the outermost orbit may change, both increase or decrease due to the interaction between the electrons of different atoms. The 6n states for L is equal to 1, which originally had identical energies. So, basically previously it was having identical energies, but now in isolated atoms, but now spread out to form an energy band. So, basically now they spread out. So, what does this energy band try to say, what does this shape try to tell us is, basically each of the electrons which are residing here are having different energies. So, this is the only thing which is being explained by using this complete diagram. It is not a straight line diagram. So, what does it try to say is basically that the electrons residing here are having different types of energy, different values of energy. Okay. So, the 6n state for L is equal to 1, which originally had identical energies in the isolated atoms spread out and form an energy band, as you can see. Similarly, the 2n states for L is equal to 0, for L is equal to 0 having identical energy in the isolated atoms split into a second band. As you can see, this is the second band here. Carefully see the region B of the figure separated from the first one by energy gap. As you can see, there is an energy gap also here. So, this is nothing but your region B, or you can say as something after region A. So, basically in region A there was isolated atoms, in region B there is a energy gap present. Also the isolated bands are converted into, let us say, a continuous band. Okay. So, this thing is also been explained. Next thing is, at still smaller spacing, however, there comes a region in which the bands merge with each other. So, let us say what happens in region C and region D in the subsequent classes. For now, let me stop it here only. So, in this discussion, in this part discussion, we concluded with the explanation of region A and region B, and also understood the chemistry behind the classification. Okay. So, let me stop it here only. I will conclude a discussion of band theory in the next part of this lecture. So, thank you so much.